Järgmised esinejad on Kristin Jõrdaal ja Fredi Garcia. Kristin on Sintefi gaasitehnoloogia osakonna vanemteaduri uurimisjuht ja Fredi on Mongstadi tehnoloogiakeskuse nõustamisteenuste juht. Kristin, tema on saanud soojusenergeetikkraadi Rootsist Lundi ülikoolist ja on töökogemusega Vattenfallist ja Siemensist, liitus Sintefiga 2004. Ta on juhtinud ja koordineerinud mitmeid Norra ja Euroopa projekte energiatööstuse süsinikdioksiidi sidumiseks, sealhulgas programmi Horisont 2020 raames. Fredi omakorda omandab magistrikraadi Prantsusmaal Ensikis protsessitehnikas. On töötanud Totalis, Prantsusmaa ühes juhtivas naftatööstusettevõttes ja nüüd viimastel aastal tegelenud ta siis süsiniku püüdmise tehnoloogiatega. So, Kristin and Fredi, if you're ready, then I'd say floor is yours.
Thank you very much, Marius. So I will begin and then Fredi will do the second half of our talk. So we will talk about C02 Capture and the technology status and R&D needs. And spoiler alert, there has already been quite a lot of R&D, but there are still some needs. But a little bit of a background that you probably are aware of already, but that the IPCC actually prescribes drastic changes when it comes to CO2 emissions in the years that lie ahead of us. That's a huge challenge. They published this special report on reaching the 1.5 degree target in 2018. And that carbon neutrality even will require quite drastic emissions cuts and even carbon dioxide removal beyond 2050, around there. EU has also followed after this, and in the Green Deal delivered really historical climate ambitions towards 2030 with 55% or lower CO2 emissions with respect to 1990 levels and net zero by 2050. And when we look at the scenarios, CCS is one of many necessary solutions that need to be applied to reach the EU climate goals. As we saw from Jörg, we can't do it with CCS alone, but it's one of the solutions that we need to apply. So it's not either or, it's the full package of solutions, actually. So to talk about CO2 capture, I'm not sure that all the audience is familiar with that is, so I will give you a bit of an introduction there. We have three technology groups that we talk about that you often see in the literature. So post-combustion capture, that is end-of-pipe capture from exhaust gas. You have the combustion or the process you separate CO2, you see the blue box, and that's it. It's a relatively simple process modification. You don't go so in-depth in the process, but often the CO2 concentration is also rather low. You take what you get from the plant, and that means that you have a fairly high energy consumption for CO2 separation. One alternative that's been studied for many years is oxy-fuel combustion capture, where you modify the air to be oxygen instead when you burn, so you don't have all the nitrogen in the process. A little bit there will be. That means a combustion project of hydrogen, carbon dioxide, and some excess oxygen. You also need to recirculate some of the CO2, which make it more complicated to control temperature. Then when you separate the CO2, the separation process requires less energy, but the oxygen separation requires energy. So it's about the same, I would say. There are differences, but Then the third pathway is what's called pre-combustion capture. In oxy-combustion, we modify the air, so we don't have the nitrogen. In pre-combustion, we modify the fuel instead. That we reform. If we have a gas, we gasify. If we have a solid fuel, to produce a syngas, which is largely CO2 and hydrogen. When you shifted it, you can remove the CO2 before the combustion, and you burn. Traditionally, you talked about burning this in a gas turbine. You need a low NOx gas turbine. These are still under development. But technologies that were developed previously for pre-combustion, we can see they are also now, that's what you can use also for hydrogen production with CO2 capture from fossil sources. And this talk will mainly be about post-combustion. We see also that post-combustion capture is really what is the most mature technology and what's largely being applied now. There is a project on oxy-fuel in cement industry, and there are a few others, but it's mainly post-combustion that's moving forward towards industrial scale now. And then how do we capture CO2? This is not the most beautiful slide, perhaps, but I'm trying to explain the principles that we have. We have liquid absorption, where CO2 can get trapped in a liquid, absorbed in a liquid. You heat up the liquid, and then you release the CO2 again. So it requires energy. For solid absorption, desorption, CO2 can get attached to a surface. You can add heat or reduce the pressure, and the CO2 will be released again where you want it, but with not so much impurities. Membranes is a third one, where you sort of filter gases. Membranes are known in many applications. You typically need a pressure level as a driving force. You filter it through the membrane. CO2 molecules are larger than many of the molecules they are mixed with in a flue gas, which is a problem, but there are membranes that can largely filter CO2 so that you have a concentrated stream of CO2. And then the fourth group we can say is phase separation. Then you need quite a high concentration of the CO2 already. You can compress it, you can cool it, and then have a phase separation so you get liquid CO2, which, for instance, can be attractive if we have ship transport of CO2, which is what's happening in Norway now. But normally you need another separation upstream of the phase separation. But as Jörg said, also that CO2 capture requires energy. And this is fundamental. That's what I want to explain with this. We can't go around this. You will need heat and or power to capture CO2. And the optimum capture technology for your flue gas with CO2 or for your source with CO2, that will vary depending on, for instance, the CO2 concentration, the pressure you have on the gas, and the temperature. So there's not a one size fits all. I'll explain that a little bit more here. That this graph, first of all, I won't go into detail on all the dots, but this is a graphic representation of the conditions at which CO2 can be captured. So it's a database of information in the open literature, both from existing plants and also from some literature studies. But if you see the lower black line says 1 atmosphere, that's CO2 that's emitted or produced at atmospheric pressure. The little orange circle is a large family of coal-fired power plants, which I believe are some more or less similar to shale oil, and the condition you would use for post-combustion capture. The gray area is pre-combustion capture, where you would have gasified the coal and then separate the CO2. And the yellow area is the conditions you would have for oxy-fuel, where we would have a much higher CO2 concentration. And up to the right, you see the red circle, maybe it should even be up at the top of the corner of the graph. That's the condition where you want to end up after you capture CO2. You need to compress it, process it, so that it can end up in a transportable condition. So again, to emphasize that there is not one size fits all for CO2 capture, because the prerequisites vary from depending on where you want to capture it. But again, amine post-combustion is the most mature. So, but other technologies are emerging. There is a lot of R&D going on. Amine is the most mature, as I said. But we see here on this graph, or this graphic representation from TCM, that we have a lot of emerging technologies at the low technology readiness level, 1 to 3, not really going to large lab scales. We have what's perhaps more interesting to follow when you're looking for applications, what is coming to lab scale and demonstrating close to industrial conditions at TRL 4 to 6, biphasic solvents, precipitating solvents, and so on. And these are, several of them are already moving towards TRL 7 to 9, where you get to industrial conditions and commercial scale afterwards. So benchmark amine scrubbing, and there are improved conventional solvents, other things really moving in this direction now. So there is a lot of R&D that's been done already that's ready for harvesting, I would say, for those who are moving in this direction with their industries and to comply with regulations that are coming. a little bit more about amine capture. This is where you absorb the CO2 in a liquid, you heat it up and you desorb it again. This is the most mature capture technology of all, or the family of different amines. And several of these technologies have already been tested at TCM. Freddie will talk more about what they have done at TCM. And the main principle is that you have, for instance, a coal-fired boiler, the big pink part in the illustration, that you pre-treat it, clean it a little bit, and then move to the blue vessel, which is where the flue gas meets the amine, so that you wash the CO2 out of the flue gas. You can emit it to the atmosphere. So this liquid then, which is rich in CO2, is pumped to the orange stripper. You heat it up and release the CO2. And to heat this up, you need steam, condensing steam. And for a power plant, you would typically take this from the steam turbine, which means that you produce less power. So that is how the energy penalty affects the CO2 capture. And for my last slide, to show a little bit more about what lies behind that we say that CO2 capture is commercial with amines. There has been a lot of R&D going on for many, many years. We knew that this worked already before, but to really get it ready for power plants and the flue gas specific environments that we have for the industries that emit CO2. There have been research from computational chemistry to bench scale testing, different scales of lab testing, to mobile test units, where, for instance, Arc and Clean Carbon have one that's been around in different sites. We can test flue gas on site before you move to decide what you want to do. And then Technology Center Mongstad has tested a lot of amines on a larger scale than this mobile test unit. And then we have the first full-scale power plant with CO2 capture. The CO2 capture came in operation in 2014 in Canada in Boundary Dam. For instance, we see now in Sweden that we will have a cement plant with CO2 capture, perhaps also a waste energy plant with CO2 capture operating in a few years. There are coming a couple of plants in the Netherlands and so on. But all this experimental also always have to be accompanied and has been accompanied with a lot of modeling and simulation evaluation of the experimental work. So these go hand in hand, both at Sintef, at TCM, and at many other places. So with that, I would like to give the word to Freddie for the rest of the talk. So,
thank you, Kristin. So, as Kristin said previously, normally before going to full scale, you want to go through a demonstrator phase. Why, you may ask? Well, in reality is that in the demonstrator phase, you can de-risk your site before going to the full size. How do you do that? Well, because you can, in the demonstrator, test the technology, you can optimize your operating modes, you can try many things and learn in a safe environment before you apply these lessons then later on the real scale. So what I'm going to do now is going to give you a couple examples of the lessons we have learned at TCM through the several campaigns we have run so far. And one of the main ones is that solvent hygiene is key for a good operation on your capture site. What you will see is that if you can maintain the quality of your solvent, your process will be very stable. You're going to have the plant availability is going to be high. You will be able to have low level of emissions to the environment, which is regulated by the different governmental agencies. You're going to have a high energy efficiency, which at the end of the day means that you consume less energy to capture the CO2. And overall, you're going to capture the most CO2 that you can, which is what you want to do. You will also see that your chemical consumption will be low, and there's always some losses of solvent with the environment in the emissions. You cannot do anything about it. What you want to do is to keep it as low as possible. Why? Because at the end of the day, what you lost, you need to compensate by putting extra solvent into the system, which costs money, of course. It will help as well as sustainable operations. I will go into more details on that later on, but just say that you will be able to operate your solvent for a longer period of time without having to add any additional chemicals or having to do any specific operations. And finally, you will be able to guarantee the integrity of facilities by avoiding problems of corrosion and fouling and eventual failure of your equipment. If you can go to the next slide, please, Kristin. Okay, So to give you an example of that, I'm going to tell you a story at TCM. This is an actual problem that arrived on site. Let me just say first that this is the worst case scenario. This is not something you want to have in a real plant. We have this at TCM because we are built for pushing the boundaries of the operation. We want to go we want to see how far we can go in the different limits, but you don't want to have this at all. So, solvent, it will degrade with time. There's nothing you can do about it. However, several parameters of the operation will impact the velocity at which it will degrade. For instance, if the temperature is too high, or you have too much oxygen, etc. When the solvent degrades, what's going to happen is going to form some solids. We call these solids stable salts. These solids will interact with your different equipment. It will dissolve the metal, so causing a problem of corrosion. And then this metal will interact with the solvent, we accelerate the degradation mechanism, which in turn will cause even higher corrosion. And so like that, you enter a downward spiral that will end up in having to shut down the facilities for a certain period of time. And you don't want to do this. Next slide, please. So the good news is that this can be avoided, and it's quite simple to do actually. Basically, what you have to do is you have to monitor the operation. Okay, you have to have a monitoring strategy. So first, you need to know which parameter to look at. You need to know how to measure it with an analytic technique, with an instrument, in which location you want to measure it, and the frequency. So part of the test at TCM has been to try to find an equilibrium between all these, trying to find the optimum monitoring strategy, between going to a very frequent monitoring, which is going to be very expensive in manpower and in chemicals, so in OPEX, and then between too low monitoring, in which case it will be useless. Okay, so this is the first thing to do. You have to have a good monitoring strategy. Next slide, please. So let's assume that indeed it shows you have a good monitor, you start seeing things that start changing. The first thing to do is just to go into your plant parameters, see if something has changed. Well, if it hasn't, well, maybe it's a normal degradation of the solvent. In that case, you want to take the necessary corrective measurement as soon as possible. The sooner you do it, the less expensive it will be for your operation. So you start doing what we call the reclaiming. So in a nutshell, it's basically you take your solvent, you concentrate all the impurities in one part of your solvent, and then this one is going to be very dirty, you dispose of it in a safe manner. The rest of the solvent, the majority of it, will be cleaned out, and you can reuse it. And you can put it back into the system and just add a little bit of new solvent, fresh solvent, to compensate for the losses. So it's going to cost you money, but not so much. Now, if it doesn't work, what's going to happen? Well, you have to say that's what I have to do at TCM. You need to change all the inventory of solvent at the same time, which is going to cost you a lot more money. And in the end of the day, if not even that works, you say, well, it's too late. There's nothing to do. I'm going to apply the last result, which is a full plant cleaning. So basically, you take out all your solvent, you throw it away, you flush everything, and then you start doing chemical washing, which is basically adding some acid into the system. And then you start asking yourself a question, what is the concentration of the acid I'm going to be using? Which one? Because if it's too corrosive, you're going to destroy your facilities. So this is something also has been tested in how to do these kind of operations. So I give you some pictures on the slides on what was the situation before the acid wash and what we had at the end. As you can see, the difference is quite significant. Next slide, please. Another lesson, a different one, is about the pretreatment of the flue gas. So at TCM, we have two sources of flue gas. One that we call dirty one. This has a lot of particles on it, right? So at the very beginning of the plant, we had a very simple pretreatment of this to remove what we could, a cycle, pretty standard, nothing fancy. So what we see when we started to use this gas is that we couldn't maintain an acceptable level of solvent emissions to the environment. It was even above what we were allowed to do. So we had to stop the operation. And we couldn't see the relationship between those two. We weren't even sure there was a relation with them. But once we had to do a modification, install this filter that you see in the picture, a very particular one. We see right away that at that moment, we start seeing that the level of amine emissions to the environment went very, very low. So since then, we start playing different parameters to try to identify the relationship between the amount of particle, the size of the particle, and the level of emission we obtain afterwards. So the conclusion is you need to know your flue gas very good in order to be able to have an adapted pretreatment for your facility. Next slide, please. Yeah, so as you have seen a couple of lessons we have about TCM, there are many, many more. We have been learning this in the past campaigns. At the time, the focus for this technology of the test was to mature the different technologies to bring it up all the way to 7, 8, 9 to be able to deploy it on industrial scale. So for those technologies, let's say all the big chunk of the work has been done. So but still there's some R&D and I that's going on those, but the focus has shifted a little bit. Now the focus is more on how to reduce the capture cost. And one way of doing this is try to optimize the way you integrate your capture plant with a specific industry. Because a waste-to-energy plant is not going to be the same as a coal power plant. It's not going to be the same as a steel factory. So what you will see is that by playing in the integration of the capture plant with your application will improve the reliability of the operation. I'm going to give you a quick example on that. If you could go to the next slide, Kristin, please. So this is a power plant case. So as you know, now everybody talks about renewable, putting more and more renewables into the power grid. When you do this, what you will see is that the amount of energy you put into the grid is going to change a lot depending on the day. If you have too much sun or too little, too much wind or too little. So you need to compensate for this because the power demand is going to be constant. So one solution for doing this is to add gas power plants into the system. These power plants have the advantage of being quite flexible. You can turn it up and down, shut it off really fast, and they adapted to these kind of stabilities on the grid. However, this is actually their business model. They need to be flexible. And when you put today and in the future even more, when you put a new power plant, a gas one, probably you're going to be wanting to also install a capture site where it associated to it. But what will never be accepted is that the power plant, that the capture site adds constraint to the operation, to the flexibility of the power plant, because the actual business model depends on that. If it's so, it will no longer be profitable. So a lot of the focus has been going on in how to coordinate those constraints, how to be able to start up your capture plant really fast, how you can accept that the charge coming from the gas turbine is going to change a lot. Maybe accept that, will be a 90% capture all the time, but sometimes some trains will be lower, but still acceptable, and it's going to be reliable. So we're all trying to minimize the time of starting up the capture site. And this kind of test, of course, you want to do it on a demonstration scale. You don't want to do it in a real site. Why? Because on the other side, there's actual users that require the electricity, and you need to be able to provide those. So you test in a demonstration in a safe environment, and then you apply them to the real site. Next slide, please. So you have seen there are a lot of knowledge available on carbon capture. So we know which technology works, we know how to build the plants, we know how to operate it. However, the success of each implementation is going to depend first and foremost on choosing the right technology for the right application. So for that purpose, you need to be able to answer this question. Typically, you need to know your flue gas, as I said previously. You need to know what's the pressure and temperature of the flue gas, what's the concentration of CO2, what's the composition of the impurities. Do you have an energy available on your site? Is going to be a new site, or is going to be an existing one that you want to adapt? In that case, maybe you have some space constraint. You cannot put whatever you want. You have a smaller place, so you have to choose a smaller technology. And then you need to know what you're going to be doing with the CO2. Are you going to store it in place? Are you going to transport it? Are you going to use it for producing something else? And in that case, does it include some constraint like you need to be very clean or dry, a certain level of pressure, etc.? So that's kind of question that usually we help answer the industry when they come see us with advisory services. And with that, I finish our presentation and we'll be happy to answer any question you may have.
Indeed, we do have a couple of questions for you guys. Let's start with the first one, which is quite specific. Walter Lotte is my most active question asker here. In your opinion, how is alum cycle combustion compared to other combustion technologies when looking CCU? So.
Oh, that's a good one. I know the alum cycle, but I've never thought about it in relation to CCU. But I think the alum cycle is a question of scale also. You can't scale it up very big. So maybe it could be useful for CCU processes because they won't be very big either in the first rounds, I guess. But I'm not up to date on the alum cycle, so I can't answer more than that. I don't know if you can say something more, Freddie.
No, I don't know much about it, no.
Well, so there you have. Do you know the largest scale that alum cycle has been applied to date? No?
No. I think the work has been done mainly in the US, right? I haven't followed that one for a couple of years. I should catch up on it.
Yeah, to my knowledge, there was some plant in Texas. It was commissioned in 2018, but I don't either remember the capacity. So, sorry, Waldur. Still. Next one. The question would be, how you think like CO2 storage versus utilization, which would be more beneficial for human society in the future? Or can you do that? Prefer one to other?
I would say you have to look at the quantities. Because there's more than enough CO2 for everybody who want to do CO2 utilization. It's going to require a lot of energy to break up this very stable CO2 molecule and make products out of it. And I just don't think we have enough renewable energy to do this on a large scale that can contribute to really combating global warming. But I think CO2 utilization can help by providing a business case. If you take some of your stream for CO2 utilization, can do it as a useful product, then that can help your capture and storage project. But I also want to say about everybody who thinks they're going to make a lot of money on CO2 utilization, that look at what happened with the SOx, sulfur dioxide reduction in coal-fired power plants. I worked with that in detail for many years, but I know I've been to coal-fired power plants and seen the desulfurization, seen all the gypsum that lies there, and said, oh, wow, this is great. You can make a lot of money on gypsum. And then I got the answer that no, the construction sector knows that we need to get rid of this gypsum. So if CO2 utilization goes on a large scale, it's more complicated because if you extract less fossil fuels, you will have less fossil carbon there. But I don't think it's going to be large compared to what we need for C02 capture and permanent storage, because we need the permanent storage. Okay. If you see at the graph, the first graph I had.
Yeah, well, thank you. Frey, do you have anything to add to that? Or was Kristin thorough?
I definitely, most of the people agree with what Kristin said, that the amounts of CO2 that we need to remove from the environment is so high that it's almost impossible to do it only with utilization. You need to use both, actually. And you could argue that what are you going to do with the carbon? You have to do plenty of methanol. I don't know how many polycarbonates in order to be able to remove all that CO2 from it. So I don't think you can do one or the other. You have to do both.
Yep, I agree in that. So, yeah, there was only one more question, that where would one use CO2, but I think maybe you answered that. But you could elaborate. Let's say we take CO2, you want to produce some chemicals or whatnots, and where would you put it?
I'm not a chemical engineer, so I can't say details. But we did a study a couple of years ago in Horizon 2020 project for cement that I was working in. I had the pleasure to lead. We saw that there are some niche products where you can make a lot of money. I think polyols were mentioned there, but the process is quite complex. It's very energy demanding, and some processes are not mature enough. But if you go for chemicals, but I also think mineralization can be a pathway to, for instance, in cement industry, if you can mineralize and create filling materials for your concrete, so that you would use less cement. Ideally, there is research and development in that direction. That would also mean permanent storage of CO2, which most of the chemicals and methanol and so on, you burn it and release the CO2 again. So, but I'm not so much of a chemical engineer. I'm not a chemical engineer, so I can't talk about different chemicals really.
I've seen most of the time you start doing base chemicals. Once you have methanol, pretty much you can do any reaction to create whatever other molecule you want. But again, it's going to be very, as Kristin said, a lot of energy is required. And then I would say the TRL for that is relatively, it's not 0, but it's not 8, 9. So the application large scale is quite difficult to do in the short term. So it's an area of development for sure, but we're not there for a large scale deployment.
Yeah, but do you see any future in that? Let's say in 2050 perspective. So eventually, if we want to change from fossil fuels altogether, then we have to find new source of carbon, don't we?
Yeah, I think it will depend on the cost of the fossil fuels, how much we restrict the extraction of the fossil fuels, because then the carbon that we already have in circulation will be more valuable. So, but I was also thinking now actually that because I kept talking about that energy demand goes down, we keep developing CO2 capture, we'll probably see the same, or I'm sure that we will see the same on CO2 use and conversion to chemicals, that we will see energy consumption going down, but it will never be 0, just as for CO2 capture. So, question is, once you have captured your very highly concentrated CO2 stream for point sources, do you want to make a fuel or chemical out of it, which eventually will be dispersed, like not from one central emission point anymore out into the atmosphere? It's extremely complicated, actually, but we'll see. To go back to what was your question, actually, if we restrict oil and gas extraction, lot CO2 that's already appeared will have a higher value.
Well, thanks for answering. Well, thanks for your presentations, Kristin, Freddie. Well, we applaud to you, and thanks again.